Hey guys, in this video I am gonna discuss what do quantum physicists mean by the term wave function in quantum mechanics. My name is Saptarshi and you are watching Cosmos Unveiled. At first, let's take a look at a little bit of history of the wave function. In the year 1924, the French physicist Louis de Broglie came up with the idea that matter can also act as waves. For example, electrons, protons, quarks, etc. can behave as waves. Then, in the year 1926, the Austrian physicist named Erwin Schrödinger took this idea and came up with the Schrödinger's wave equation. So what is a wave function? Well, wave function is a complex valued mathematical function which stores all the information that can be known about an isolated quantum system. The word complex doesn't mean that it is not simple. It just means that it is of the complex form. So at first, let's discuss what are complex numbers. A complex number z is of the form x plus iy, where I square equals minus 1 and x and y belongs to the set of real numbers. This representation of complex numbers is known as the Cartesian form. There are also two other forms to represent a complex number. To learn them, let's look at this graph. The graph is plotted in the eigenplane, which consists of two axes, the real one and the imaginary one. Here the complex number z equals x plus iy is plotted, whose coordinates are x, y. Let's transform it into polar form. The distance of the complex number from the origin is r, and the angle which it makes with the real axis is theta. So its polar coordinates are r, theta. So we can write the complex number as r cos theta plus I sin theta, where r equals root over x squared plus y squared and theta is the argument of z. Well, what do we mean by argument? I will discuss that later. There is another form to represent a complex number known as the Eulerian form. Just know that e to the I theta can be written as cos theta plus I sin theta. Now let's discuss some important properties of complex numbers. At first, the modulus of a complex number. It is basically the distance of the complex number from the origin in eigenplane. If z equals x plus iy, then modulus of z equals root over x squared plus y squared. If z equals r cos theta plus I sin theta equals r e to the I theta, then the modulus of z is r. Here's a brief representation of what I said. Then there comes the amplitude or argument of a complex number. It is basically the angle which the line joining the origin and the complex number makes with the positive real axis in the eigenplane. It is represented as arcz or ampz. Say we take a complex number z equals x plus iy, whose coordinates are x, y in the eigenplane. Then we join the complex number with the origin by a line. Then the angle which the complex number z makes with the real axis is known as the argument of z. These are the rules which you need to apply to find the argument of a complex number when it is in any of the four quadrants. The third property you need to know is the complex conjugate of a complex number. To know this property, at first you need to know that there are two parts in a complex number. The real part, this part is called the real part, and the imaginary part, this part is called the imaginary part. The one associated with I is known as the imaginary part. Just like that, in the polar form, r cos theta is the real part and r I sin theta is the imaginary part. So what is the complex conjugate of a complex number? It is actually the image of that complex number with respect to the real axis. Say we take a complex number z equals x plus iy, then its image or the complex conjugate will be z star equals x minus iy. Well, how do we get that? Just flip the sign in front of the imaginary part. If it's plus, flip it to minus. If it's minus, flip it to plus. Z and z star are both the complex conjugate of each other. The last three properties which you need to know are modulus of z equals modulus of z star, z times z star equals modulus of z squared, and the complex conjugate of z star equals z. There are many more properties of complex numbers, but these are the only ones you need to know to understand this video. Now let's come to the wave function. As the wave function is a complex valued function of a real variable, it can be represented in the form psi of x equals u of x plus I times v of x, where u and v are real valued functions. Since the wave function or psi of x is a function, it takes input and gives us some output. The inputs are generally some measurable physical quantities like position, momentum, etc. But the output is not directly useful. To make the output useful, we use the Born rule, which was given by the physicist named Max Born. So what does the Born rule state? Well, it basically states that if we take the square modulus of the output, then we get the probability density of the corresponding input. Well, what does that mean? See, position is given as our input in the wave function. Then we get the probability density of finding that particle at that point in space. To understand this concept, let's take our arbitrary wave function and plot it in a graph. Well, this graph tells us nothing. But if we take the square modulus of the wave function and again plot it, it gives us the probability density of that corresponding input. Well, by taking the square modulus, we make it positive, and probabilities are always positive. You cannot get negative probabilities. You cannot say that the probability of getting a head in a coin toss is negative 1/2. But there are some criteria which need to be fulfilled for a wave function to be meaningful. A wave function must be finite everywhere. There shouldn't be a point in the graph where the wave function is undefined. It must be continuous everywhere. There shouldn't be any discontinuities. And last but not the least, it must be square integrable, which means definite integral negative infinity to positive infinity modulus of psi x squared dx equals some finite quantity. But what does the wave function actually mean? Is it just a mathematical tool to find probabilities, or it has some other deeper meaning? Well, people differ on how to interpret it. According to the most famous interpretation of quantum mechanics, the Copenhagen interpretation, the wave function is just a mere mathematical tool. But what is actually waving in the wave function? In case of light, the electric and magnetic fields are oscillating. In case of water waves, water is oscillating. But what is waving in the wave function? Well, you can think of the probabilities waving here. But how do we get to know about a system's wave function? Well, we simply solve the Schrodinger's wave equation. It tells us how the wave function looks and evolves over time, if it's the time-dependent version of the Schrodinger's wave equation. Well, that's all for today. See you in my next video.